Today we will look at extrema on an interval. So the objective is understanding the definition of extrema of a function on an interval, understanding the definition of relative extrema of a function on an open interval, and then how do we find extrema on a closed interval? Well, we first want to understand what is an extrema. I mean, we're going to be working with extrema of a function. So when we speak of extrema, what are we really talking about? So let's try to understand what is extrema. So when we talk about extrema of a function, we're really talking about the highest point and the lowest point of the function, right? And remember height, we talk about y value. So if you look at this graph that I have drawn here, okay, let's call this figure A. Okay, so you will notice that this point here, okay, is the lowest point. And since this point here is defined, it's filling, this point here will be your highest point. So the lowest point ever, it's absolutely the lowest point. This point here is what we call our absolute minimum. Yeah. And the highest point, since it's absolutely the highest point, so this is what we want to know about. This is called your absolute maximum. So it is called the absolute because that's the highest possible point on the graph. Okay, it's absolutely the highest point, no questions. Okay. On the other hand, if we look at this, so we call the figure B, notice that the endpoints are open. So there is no maximum here, but we do have a minimum, okay? This here will be some minimum point. There is no max because this is open. Open, no max. Okay. So the point has to be defined, and we'll get into the definition in a few minutes. Okay. Now, there is a difference between what we call absolute minimum and relative. Okay. So the minimum and maximum function on an interval are the extreme values. Or extrema is a singular form of the singular form of extrema is extremum. So if we only have one, we have an extremum. So when we speak of extrema, we're talking more than one. Okay. So here we only have an extremum. Okay. So as you can see, the graph really differentiates if there's a max, if there's a min. Now here's something I'm interested in. I'll give you the definitions in a minute of what these things are. So if we look at another picture, let's call this figure C. So if we look at figure C, the absolute, clearly here you can see that the absolutely highest point on this graph will be this point here. So this is the maximum point on the graph. Okay, maximum. And it's the absolute maximum. Okay. The absolute minimum point in this graph will be that. That is the lowest point possibly. So this is the absolute minimum. Now there's some other points. If you notice, there's some other points on this graph. There's a point here. There's a point here. Okay. Now there's something else for this point. This point here is known as a relative minimum. Now, when we talk about relative min, as I said, I'm going to give you the definition in a few minutes. A relative min is relative to the points around it. So when you're talking about relative min, you have to compare that with points around it. So if you look at this point here also, this point here also will be considered a relative min. So although it's an absolute min, it's also a relative min. So because this point here, let's call this point A, okay? I'm going to call this point A and this point B. Because A and B has surrounding points and it's the lowest point around those surrounding points, they're called relative min. So that brings us to this point. If you look at this point C, that C point is a high point relative to its surrounding points. So this point here would be a relative max. Okay. Now this point here that you're looking at, okay, if we look at this point here, this point is not a max. Okay, it is not a relative max because you can find points to the left of it, but you can't find points to the right. So it's not a relative. Okay. And it's not the maximum point because there are higher points above it. If you look all the way to the left of the graph over here, okay, that's higher. So it's not an absolute max. So that's just some point. Okay. So you have to be careful when we speak of relative. Relative means you're comparing it to some interval. It's the highest point on an interval. So if we look specifically at some interval over here, let's say between here and here, then that green dot is the lowest point within that interval. And we'll get to definitions in a few minutes. Let's look at one more example before I write the definition. So in figure D, what's the highest possible point on this graph? Okay, highest possible point. So if you look over here, let's call that point A. This is the highest point, so this will be your absolute max, the highest possible point. Now, if you look at point, let's label all these B, C, D, and E. D is lower than all of them, but the point is not defined. Okay, so this is not a minimum because the point is not defined or exist. Okay, there's a hole in the graph there. Now, if you look at the point C, if we look at the point C and the point B, okay, are there surrounding points about those points C and D? Okay, so let's look at them individually. This point here, since it's low, this will be a relative min. This here will be a relative max. Once again, because I can look to the left of it and I can look to the right of it. Now, if you look at E, we can look to the left and we don't see anything. But we look to the right, there is a graph. So E is not a relative max or a relative min. Because for relatives, you have to be able to look to the left of it and to the right of it. Okay? Both sides. In this figure, we show relative max and relative min. Okay, and here we have the definition of the extremas. Remember, extrema just tells where is there some high point or low point on the graph. And we have seen from the first pictures or the series of graphs, we talk about absolute min, absolute max, and then I introduced to you relatives. Okay. So it is very important to understand that when you speak of relative, okay, the relative point means that there is some surrounding points. You're comparing it with surrounding points. So you're looking to the left of it and you're looking to the right of it. Okay. Always. So, and that is why the end point, right? Usually the end of a graph, if that's the end point, it will never be a relative. Okay. Endpoints cannot be relative. So you will note, okay, note the end point of a graph cannot be a relative min or relative max. It's impossible. And the reason why that's the case is because if you look at the picture here again, okay, you will notice that there would be no comparison either to the left or to the right. Okay, if we look at this picture here, okay, although this is the highest point, okay, it will not be a relative because you can look to the left of this point, but there is nothing to look on the right. And for a relative, you have to be able to compare it. It's relative to the left side and the right side. Okay. For example, this point here and this point here would be relatives. So this point here will be a relative max because you can compare it from the left and from the right. This will be a relative min because you can look from the left and from the right. Okay. And this point here will be absolute min. And then this point here will be absolute max. Okay. So that's the difference between the two. The relative is that you have to look from the left, and the right, it's relative to points surrounding it. Okay. Relative to points surrounding it. That's very important to note. So let's look at critical numbers now. So you should have noticed that the slope, okay, at these relative points, relative extremas, so meaning maximum or minimum, okay, you should have noticed that the slope at the relative extrema is 0 or undefined or does not exist. Okay. The x value at these special point or points are called critical numbers. Okay. So if I show a picture here to briefly discuss the two situations we're talking about. And let's look at two basic functions that we're well aware of, the absolute value function. Okay. So notice that at this point here, okay, at that point, we have a relative min. Function is continuous, and the slope m there is undefined. Okay, because the slope from the left and the slope for the right. Okay, it's different slope. Slope is not defined, meaning that the first derivative there doesn't exist. Okay, it's not differentiable at that point. On the other hand, right, the slope is 0. If we look at this figure here, just the basic parabola, you will notice that just at this point here, which is also a relative min, that the slope m is equal to 0 because the tangent line at that point is 0. Okay. And that's where we're saying that you should have noticed that the slope at any one of these points is either 0 or doesn't exist. If you go back to any one of these, you will notice the same for each one of these points that we have here. The slope is 0 or the slope doesn't exist. Okay. So that brings us to the definition of what we call the critical number. So the definition tells us that let f be defined at c. We take the first derivative and we set it equal to 0. Okay, take the first derivative, set it equal to 0. And I'm going to list the steps in finding the critical number. There are usually 4 steps. If f prime of c is equal to 0, or if f is not differentiable at c, then f at c is a critical number. Okay. So we can look at examples of that. So we solve for x squared, right? Let's look at a very similar or basic examples. Example. Find the critical number. Well, if you think of this, let's say f of x is equal to x squared. Well, we know what the picture of x squared looks like. If we draw the graph of x squared, which is a parabola, okay, the graph of x squared we know is this graph here. Okay, that's the graph of x squared. And we see that there is a minimum there. That's a relative min. From graphical observation, we can see that. Okay. So we know that that point is a relative min, and that point we know is 0, 0. So c, right, it's the x value. C is equal to 0, which is equal to the x value. Okay. So now let's see algebraically if we can figure that out, right? So we're saying first we want to find f prime. So step 1 is, what is f prime of x? What is that equal to? Well, f prime of x will be equal to 2x. Okay, that's the first step. Okay. And then we want to take f prime and set it equal to 0. So we can say second, set f prime of x equal to 0. So we have 2x is equal to 0, therefore x is equal to 0. And here we saw that this is true. Okay. Why? Because at that point here, at c equal 0, which is the same as x, m is equal to 0. So the slope is 0. Yeah. So there's a bunch of things happening there. So here are the guidelines for finding extrema on a closed interval now. Okay. Because on a closed interval, we have a little bit more work to do. So here are the steps or the guidelines for finding extrema now on closed interval. Okay. So we can look at an example of this, and then let's go through the steps as a group, and then we'll see what happens. Now you have to be careful. Remember, the definition says that the function must be continuous, okay, and the slope has to be 0 or undefined. Okay. So the slope has to be 0 or does not exist. So you have to be careful. Okay. Because you'll see in a few examples that, you know, if f is defined in C, and if f prime of C is equal to 0 or f is not differentiable, then C is a critical number. That's the definition. Very important. Okay. So let's look at some scenarios, examples. Okay. Find the extrema of f of x equals 3x to the 4th minus 4x cubed on the interval -1 to 2 inclusive. Okay. Now note, right? You should note here, note, interval is closed. Okay, the interval is closed. So if we go find the critical numbers, okay? So first, step 1. Okay. So f prime of x will be equal to 12x cubed, okay, minus 12x squared. And now, if we find the critical numbers, which is evaluate each critical number. So we haven't got to step 2 yet. So the critical number is f prime of x equal to 0. This means that 12x cubed minus 12x squared is equal to 0. We can factor out 12x squared, leaving us with x minus 1 equals 0. So 12x squared is equal to 0, and x minus 1 is equal to 0. So x is equal to 0, and x is equal to 1. These are your critical, these are the critical numbers. And I'm going to put possible, okay, possible critical numbers. Now, and there's a reason we said possible, because is, you know, is f of 0 defined, and is f of 1 defined? Okay, that's why we say possible. Because sometimes you're going to find critical numbers and you will have to ignore them at some point. Okay. Now, because this was a closed interval, okay, so what is f of 0? So this is really the step 2. Okay. F of 0 would be 0. And f of 1, okay, would be -1. So they are defined. Now, what we have to do is evaluate f at each endpoint. So these were the critical number. Here we now look at the endpoint. The endpoint given was what is f of -1 and what is f of 2. These are your endpoint. So f of -1 would be 7, okay? Which means 3 times -1 to the 4th minus 3 times -1 cubed. So this becomes 7. So f of -1 is 7. And then f of 2 becomes 3 times 2 to the 4th minus 3 times 2 to the 3rd, okay, which is equal to 16. So f of 2 is equal to 16. So if we sort of make a little table, okay, if we make a little table here, and this is just a matter of style, I like the table. If we call this the left endpoint, okay, then we had two critical numbers. So critical number, then we had another critical number, and then we had the right endpoint. Okay, so just a little way I like to do it. It kind of like put stuff where I can clearly see what it is. Okay, so the left endpoint, we know that x is equal to -1. So the critical number, we found two critical number. The critical number was 0 and 1, and the right endpoint we know was 2. So what we're going to do is fill in these things here. What is f of -1, which we did. F of -1 we know. Okay, f of -1 is 7. Okay, then we have f of 0, which is equal to 0. Okay, then we had f of 1, which we know is -1. And then we have f of 2, which is equal to 16. Now of these, remember 7, 0, -1, and 16 are all y values. Okay, so which is the smallest? Okay, and which is the largest? Well, the answer here would be -1. And the answer here will be 16. Therefore, okay, therefore, at x equal 1, okay, and at x equals 2, okay, we have a minimum here and we have a maximum here. Okay, so one of the critical number does not yield any relative min or relative max. Okay, x equals 0 does not. And this is why we have to be careful, because not always the critical numbers, and that's the reason why I said possible, okay? Not all the critical numbers will give you a relative min or a relative max. And you have to be careful with that, extremely careful. So every time you do a problem or you do some sort of a check, you must always look and confirm if it is. So I mean, graphically, it really tells a lot, you know. So sometimes if you can mentally look at the graph or figure out what the graph is, you'll be able to tell. For example, let's find a critical number. Or numbers, okay? Given g of x is equal to the absolute value of x, okay? Well, if you do this algebraically, it will take some time, okay? Because you have to take the derivative, okay? Now, take the first derivative, set it equal to 0 to find your critical numbers. But you know, okay, let's look at the graph, okay? So if you look at the graph of x, of the absolute value of x, we all know what that graph looks like, okay? You know what the graph of the absolute value of x looks like. And that is the v, okay? Now, notice that at this point here, there is a relative min, okay? And because there is a relative min, there will be a critical number, although m is undefined, right? M is undefined, okay? M is undefined. So relative min at x equals 0. Now, is that a critical number? Well, is x equals 0 a critical number? Well, is g of 0 defined? Is it? And if it is, then the critical number is 0. So what is g of 0? Well, it's the absolute value of 0, which is equal to 0. Therefore, x equals 0 is a critical number. Okay. So sometimes it really helps to look at the graphs to know what's going on, if you can possibly see it, but make sure you always perform this check, okay? Very important, when you get your critical number, you have to check it. You must. Let's look at another example, and probably I will close off with this example for today. We want to find critical numbers. So find all critical numbers. Okay, here's an example. Given g of x is now equal to x to the 2/3 power. So the first step is, all right, step 1, we go through the steps. What is g prime of x? Well, g prime of x will be 2/3 x raised to the 2/3 minus 1. So this comes out to be 2/3 x to the negative 1/3, which can be written as 2/3 x to the positive 1/3, or you can write the cube root of x, okay? Let's rewrite that. 2/3 x to the 1/3 power, okay? Now, if we look, or we try to find a critical number now, what is g prime of x equal to 0? So we have 2/3 over x to the 1/3 power equal to 0. Or you can write 2/3 times the cube root of x equals 0. Well, we can solve for x here, probably performing a lot of ways. First thing I could do is get rid of the fraction, okay? So if we have 2/3 x to the 1/3 equal to 0, I can multiply both sides by 3/2 if I want. 3/2, I said. So this will cancel out. So we have x 1 over x to the 1/3 power is still equal to 0. And then another way of writing this is the same as x to the minus 1/3 power equals 0. So we can raise now each side to the 3rd power. So we have x is equal to 0. But the function is undefined. Note, right? G of x, g prime of x is undefined at x equals 0. So what are we saying here? That are we saying that, so the big question is x equals 0 a critical number? Okay. Well, and remember, to find that out, we go now check what is g of 0. So g of 0 is 0 to the 2/3 power, which is equal to 0. So since we are able to plug this in, the critical number, right? Critical number is x equals 0. So many examples, try them for what we'll post for homework. Okay, you want to do as many examples as possible to see what's happening. Okay, thank you.